Hello everybody. In this screencast I want to discuss how we can use a standard or calibration curve in order to determine the value of some unknown samples. So for example, we have an unknown protein concentration in our sample. We want to find out what this unknown concentration is. So what we do is we usually prepare a standard with known concentrations and we measure the absorbance of these standard samples. And from these absorbances and the correlation between the known protein samples and their absorbance, we can then try to figure out what is our unknown substance. So basically what we want to do is we want to have we want to create a standard curve. So here we have the amount of protein, say in micrograms, and here we have the absorbance. So for example, we could use a Bradford assay, and what we find is something like that. So that is from our standard curve. That is the standard curve. And now we can say we have an absorbance of our unknown samples. So we can say here is the this is the absorbance that we get from our unknown sample. So unknown. And all we need to do really is we follow our unknown sample, and where it hits the standard curve, we can see that this value here, this would be the protein amount in our unknown sample. So even without knowing any absorption coefficients or extinction coefficients from a standard curve, we can very easily figure out what is the concentration, what is the amount, or whatever we are looking for in our unknown sample. So how are we going to do that in Excel? Well, most of you are familiar with the concept of a trend line. So what we can do is I've got here my standard with the known concentration or known amounts of a test protein. So I've got anything from 0 to 10 microgram of bovine serum albumin. And in a Bradford assay, I measure the absorbance in a spectrophotometer. And what I can do now is just simply do what is known as a regression line. So I go to Insert, and I find the right chart. So I use a scatter plot like this. So here would be my plot for this, and obviously we would have the axis properly labeled. So on the y-axis we have here absorbance, and on the x-axis we have our microgram of BSA protein. So what I get here is a nice standard curve, and I can actually try to do a best fit line, and the way to do that is just simply right click with the mouse on one of the data points, add trend line, and it will come up with another window here. So we can display the equation on the chart, and we can also display an R² value. So we've got the data here, and let's close that window. So we get the equation for our trend line here for the standard. And what we see is that the slope, let me write this down here, the slope, this would be 0.0518, and the intercept for our trend line would be plus 0.0014. Okay, so these are the data that we have. Let me make this a little bit larger so that we can see it properly. Okay, and now what we can do is we can say, right, here are our unknown samples, or the absorbances for the unknown samples. Now what we can do is we can calculate an average of these unknown samples. So because we have got a count of 3, we have 3 samples, so we calculate the average. Now all we need to do is start typing. The average of these samples is 0.2033. Okay, so that is our average. And again, let me make this a little bit larger here. So what we can say now is basically we have an 0.2 absorbance. So what does that actually equate here? So what protein amount from our standard does 0.22 equate? So we can see it's probably a little bit above 4 micrograms. So how can we actually calculate that? We know that the equation for our standard curve can be expressed as y equals mx plus c. So we have our slope, we have our intercept, so we also have our y, that's the average that we just calculated, and what we want to know is now the corresponding x value on the microgram BSA axis. So we can very easily rearrange this equation and can say x equals y minus c divided by m. So what we need to do is we just simply take our average and do the calculation. So we take the mean of our samples minus the intercept, this one, divided by the slope, and we get a protein concentration of, let me just make this a little bit bigger again, we get the protein concentration, our unknown concentration, as 3. Well, let's just simply say 3.9 microgram. So we have 3.9 microgram. So the absorbance that we had of 0.2 is equivalent to around this range here. Why is it not 4? Why is it not a little bit above 4? Well, what we see is that our standard curve is the values on the standard curves are not all exactly on a straight line. So there is some variation in the standard curve. So therefore, we need to be careful what we think, what we say about our value. Because we know that we have the standard curve, we could have put the standard curve also slightly different, or maybe like that. So there is variation in the standard curve, and this is just simply due to sampling error. So it would be really more appropriate if we just simply said, well, we believe that our true value for our samples, and remember, samples are always part of a larger population, we believe that the true value, I can't even write properly, is probably 3.9 microgram plus minus a certain margin of error. That would be probably a better way of expressing what our readings actually represent. Now, these margins of error, it's not for the faint-hearted to calculate. So I've written a little program, and the link to that is in the description below, where you can actually enter your data for the standard curve and for the for your unknown samples. So this is here. So here the X values represent the microgram of BSA, and the Y values represent the corresponding absorbances. And here you have the unknown samples that we discussed, and what the program will develop and calculate for you. And again, the link to the website with this program you can find in the description of this video. So what this program calculates is a 95% confidence interval for the X value of the unknown sample, and we get here, let's round this a little bit, equals 3.9 plus or minus 0.5 microgram BSA. So we believe that the true value for our reading is somewhere between 3.9 minus 0.5, that is 3.4 microgram, and 3.9 plus 0.5, so that would be 4.4 microgram of BSA. That is our confidence interval, and we are fairly confident that when we did this experiment loads and loads of times, this would be actually the true mean, the true value for readings when we did this experiment millions of times would be somewhere between 3.4 and 4.4 micrograms. Now you see, despite having a pretty good standard curve here, we have quite a considerable span in our readings. So let me indicate that. So 3.4 is probably here, and 4.4 is probably here. So our reading of 0.2 here would give us, and we have several readings here, would give us this range here for our true population mean of our reading. So I hope this makes sense, and as I said, I post the link to the website in the description. So thank you very much for watching, and I hope you enjoyed that.